Welcome to this video series on random matrix theory. Random matrix theory has become an important tool in modern data analysis because many data sets can naturally be represented as matrices with random entries. The central question in RMT is surprisingly simple. What can we say about the eigenvalues of these random matrices? Throughout the series, I'll motivate the theory using application from statistics and data analysis. This is mostly a mathematical series, so some of the videos may involve some detailed derivations. I'll try my best to explain the intuition and work through the mathematics step by step. This series only requires linear algebra, basic statistics, and calculus to follow. So let's begin with one of the most fundamental results in the field, the Wigner Semicircle Law. It describes the eigenvalue distribution of one of the simplest random matrix model. We'll use that as a starting point into the world of RMT. Okay, so let's get started. In order to understand the Wigner semicircle law, let's think about how to build a random matrix. So the Wigner matrix is a random matrix with a pretty simple setup. So it starts with an n by n matrix X. The entries of this matrix is random. The conditions that X need to satisfy are pretty minimum. The first is that X need to be symmetric, which means that Xij is equal to Xji. This implies that only the entries above this diagonal line are free variables. So it means that in total there will be n times n plus 1 over 2 free random variables. Then the next condition is that these free random variables are independent. And we also want the expectation of the entries being 0 and the variance of the entries being 1. So that made up for a Wigner's matrix. So notice here that it doesn't really care about the distribution. So what it means that this Xij can be any distribution, such as Bernoulli or Gaussian, or any distributions we want. Right? It doesn't care about the distribution. So we just want a n by n symmetric random matrix. In the case of the Bernoulli distribution, this Wigner matrix is particularly simple, right? We just have the plus 1 to minus 1 for each of the entries, right? For example, it can be something like this. And then we just flip the entries to the other side. So this Bernoulli distribution will satisfy the mean 0 and variance 1 condition, right? That's how we can set up for the random matrix. So the central question that RMT tries to answer is surprisingly simple. We care about the eigenvalues of this random matrix. And because the matrix is random, the eigenvalues are also random. But what's remarkable is that as n goes to infinity, the distribution of the eigenvalue will converge to a deterministic distribution. For example, I have generated the eigenvalue distribution for this random matrix. Okay, so let me just grab the picture. Okay, so this is the distribution of the eigenvalues for the Wigner matrix. I chose n equals to 1000 in here, I think. And this is the distribution coming from the random Bernoulli distribution. So see that it got a pretty remarkable shape. This red curve here is a semicircle. And this histogram here shows how many eigenvalues falls into this particular region. So interestingly, the distribution of the eigenvalues will converge to this semicircle. And this is exactly Wigner semicircle law. Okay, so let me just write out the statement of the theorem. So the statement is that for Wigner matrix, as n goes to infinity, remember that X is an n by n matrix, then the distribution of the eigenvalues so actually in here we need to divide the matrix by 1 over square root of n. Right, so this distribution will approach a semicircle density. That is given by the equation rho of lambda equals to 1 over 2 pi and then square root 4 minus lambda square. So lambda is a variable in between minus 2 and 2. So this is the statement of the theorem. So see, a very interesting here is that we have the square root of 1 over n in here. This happens to be the same as CLT, the central limit theorem. So in CLT, right, we have so when we have like x1 to xn as IID random variables, then if we just sum them up and divide that by the square root of n, right? So that will just convert to a normal distribution. Right, let's say that the variance is 1, so this will just converge to a standard normal distribution. And very interestingly, in the case of random matrix, when we have the entries of the matrix being independent, with mean 0 and variance 1, we also need to divide that by the square root of n for it to have a deterministic distribution for the eigenvalues. Okay, so for the next part of this video, let's think about how can we derive this Wigner semicircle law. Okay, so in order to prove this semicircle law, we're going to first introduce a very important idea in RMT. That is the resolvent. So the resolvent of the matrix is defined as x minus z times I, and we take the inverse of it. So it turns out that the distribution of the eigenvalues can be revealed by the resolvent. And then we also want to define m of z to be 1 over n times the trace of the resolvent. So that equals to 1 over n times the sum. So we know that for the property of the trace, it actually equals to the sum of the eigenvalues. And in this case, it equals to 1 over n times 1 over lambda I minus z. So the reason we care about this is that as n goes to infinity, because if you look at this, it is an average. And lambda I is sampled from a distribution of the eigenvalues, we think. So this will just converge to the expectation of 1 over lambda minus z, right? And we can write that as an integral of rho of lambda over lambda minus z, and then d lambda. So see that this formula here looks like a transformation. This is called a Stieltjes transform. You can think of this like resembles to the Fourier transform, Laplace transform, or the or the generating function, right? Basically, we just transform the space from lambda to z, right? With this with this resolvent technique and the Stieltjes transformation. So the main idea that we want to define this Stieltjes transformation and the resolvent is that this m of z is kind of like a scalar function that summarizes all eigenvalues. So instead of tracking n eigenvalues for a matrix, right, which can be very hard, now if there's a way to solve for m of z, we kind of solved for all the eigenvalues. So the big picture for the proof is that we start with the random matrix X, then we want to solve for m of z with an equation, right, from which we will use the resolvent R of z to obtain the relationship between m of z, and then we can use the inverse transformation to get the density function rho of lambda, where we use the inverse Stieltjes transformation. So that's the idea for this derivation. Okay, so in order to solve for m of z, let's just spell out the resolvent. So notice that we have an inverse in here, right? Okay, so for the resolvent, we have 1 over square root of n x11 minus z, and then we have 1 over square root of n x12 to 1 over square root of n x1n. And then I'm not going to write out, and I'm just going to write out the last row, which is 1 over n x n1, and then 1 over square root of n x n2 to 1 over square root of n x nn minus z. And then we're going to take the inverse of it. So that will just equals to, let's call this R11, R12, and then R1n. So here is Rn1, Rn2, and then Rnn, right? And because we are only interested in the trace of this matrix, right? So that means we're only interested in these diagonal values. We don't really care about the off-diagonal values. So it would be nice if we can just directly write out the formulas for the diagonal entries. And it turns out there's a nice formula for it. It is called Schur complement. So the formula is that when we have a matrix in this block form, let's say that we have A in here, and then B transpose, and then D. If we want to take the inverse of it, let's say that X inverse, and then if we are only interested in the first entry, that equals to A minus B transpose D inverse B. And we take the inverse of it. Okay, and actually in the special case where we just take out one row, right? So this is scalar, so we can just remove, I can just remove this inverse as 1 over this thing, right? So now using this formula, we just have a closed form formula for R11 to Rn, right? So that's going to help us to solve M of z, which we'll see in a second. Okay, so let's do that. Let's just plug in the equation for Schur complement. So we will have R11 equals to 1 over. So basically we'll have 1 over square root of n x11 minus z minus. And for the next part, I'm just going to write out this part into the scalar expansion, right? That's going to be easier to deal with. So we'll have the double summation. Let's call one entries I goes from 2 to n, and then we'll have j from 2 to n. And then so I can merge the square root of n as 1 over n in the front. So then I'll have x1i times x1j. Okay, so basically I'm just separate out this part and this part, and then we'll have and then we need to take the inverse for this part, right? So notice that the inverse for this part is just the matrix R excluding the first row. So I can use this notation as R excluding the first row, right? So basically this inverse here, you can think of just that as a resolvent for the matrix when we just remove the first row and first column. So that's what it is. Okay, so this formula feels pretty complicated, but it will simplify, I promise. So it turns out that this part in here, so it turns out that this will just become 1 over n times the trace So it just becomes 1 over n times trace for the resolvent when we remove the first row. So that is nice, because when the matrix is very large, we don't really care about the matrix losing or gaining one row or one column. So this just become 1 over n times trace of R. And that just equals to M of z. Okay, but now let's just do it a little bit carefully to see why this is the case. So you have 1 over n times sum over I, and then sum over j, and then x1i, x1j, and then we have the r, ij. I need to add the subscript ij in here. Okay, so for this double sum, we can actually separate out for the case where I equals to j times the case of I equals to j. Then we have x1i square rii plus the case of I not equal to j. So the reason that we want to do this separation is because we want to use the property of the matrix entries, right? It has mean 0 and variance 1. So that's the property we want to use. So recall that we have the entries expectation of x ij equals to 0, and then the variance of xij equals to 1. Right, so what this means that the second moment for the expectation of x1i square equals to 1, and then when we have two entries, right, because of independent, so x1i times x1j equals to 0. And using this property, we'll see that the first term, let me just move this down a little bit. So this first term in here, that will just converge. So it will just converge to the expectation, which is 1 over n times the sum of Rii, right, which is just 1 over n times the trace of R, right? And then for the second term, it will just converge to 0. And this is the reason why we can just replace this entire term with m of z, right? By using this, we can just simplify this equation a lot, right? So R1 just basically becomes 1 over square root of n times x11 minus z minus m of z. Also notice here that this 1 over square root of n x11 goes to 0, right? When n goes to infinity. So that just become 1 over minus z minus m of z. Okay, so now this equation is very neat. And because of symmetry, so basically all the diagonal values, right, will have the same 1 over minus z minus m of z. Okay, so now from this, we can actually obtain an algebraic equation for the Stieltjes transform, right? So we have m of z that equals to, so that equals to 1 over n times the sum of the diagonal values for the R matrix, the resolvent, which equals to 1 over n times 1 over minus z minus m of z, which equals to 1 over minus z minus m of z. So this is super nice, right? Because we obtain an algebraic equation for the Stieltjes transform, right? Have m of z in here and m of z in here. So we'll just have m of z plus 1 over z plus m of z equals to 0. And then that means m of z square plus z times m of z plus 1 equals to 0. So this is just a quadratic equation. So we can solve m of z as okay, so that is the key equation we have. And recall this is related to the density for the eigenvalues, right? You have the rho of lambda over lambda minus z d lambda, right? And now we can apply the inverse transformation to obtain a rho of lambda, right? However, this is the part where the algebra can get a little bit slippery. Okay, so the thing is that if you look at this formula a little bit carefully, right? So we have the lambda minus z as the denominator. Because this denominator becomes 0 if z equals to lambda, and that becomes a problem. So basically, it's just saying that inside the probability density, we cannot really have z equals to lambda, or this integral will just blow up. So as a result, the correct way to look at this resolvent is that this is in fact a complex function. So this is the key, right? So mz is complex. So it can map from complex number to another complex number. We want to nudge this variable z along the imaginary axis a little bit so that we won't have the problem of this integral blows up as it approaches to lambda. But we need to do a little bit more derivation to see how it works, right? Okay, so let me just get some space. So the key question we want to answer in here is that how to obtain the inverse Stieltjes transformation. Right, so recall that our m of z equals to rho of lambda over lambda minus z d lambda. Okay, and this is a complex function mapping from complex number to another complex number, right? Let's say that z equals to u plus iv, right? Then we can just spell out this transformation as rho of lambda, and then we have lambda minus u minus iv d lambda. So we can use the conjugate to separate out the real part and the imaginary part. So the real part, so we can, okay, so let me just slow down a little bit. So we have the rho of lambda times lambda minus u plus iv. And then for the denominator, we'll have lambda minus u square plus v square, right? And that's over d lambda. And then the real parts become rho of lambda times lambda minus u over lambda minus u square plus v square. Okay, so for the imaginary part, we'll have plus I times rho of lambda times v over lambda minus u square plus v square d lambda. I know this feels a little bit complicated, right? But a very interesting thing here is that for this imaginary part, so this particular function, right? If you look at this particular function here, so that will become a delta function as v goes to 0. There's also a constant pi, I think. So it turns out that this is the key for how we obtain the inverse transformation. So I'm not going to derive this this particular function becomes a delta function, but you can check for it, right? You can check for the property of the delta function to see if it works. So it turns out that for the inverse transformation, if we want to obtain the density function rho of u, so it turns out this just equals to a limit as v goes to 0, and then we will have, and then 1 over pi times the imaginary part of m of z. So you can see that using this integral, right, and the property of the delta function, right? So this just equals to 1 over pi and limit v goes to 0 times the integral rho of lambda times v over lambda minus u square plus v square d lambda, right? So we know that this entire thing becomes the delta function of lambda minus u, right? And then for the delta function, right, for the property of the delta function, we have the integral of rho lambda times delta lambda minus u d lambda equals to rho of u. So that's the inverse transformation from which we can obtain the density function. It's by using this equation in here. Let's apply this to the Stieltjes transform m of z to see what's the density function we have for this for the Wigner matrix. Hopefully, we'll see the semicircle law. Okay, so now all we need to do is to plug in the solution for the Stieltjes transform to obtain the density function, right? So for this transformation, we have m of z equals to minus z plus square root of z squared minus 4 over 2, right? Or plus or minus. Okay, so there's one more thing we need to fix, right? Because you see that we have the plus or minus here. This function has two branches, but it turns out that only the plus one makes sense. So this is because for the Stieltjes transformation, we have m of z equals to the integral rho of lambda over lambda minus z d lambda. And when z become very large, it become, so this behaves like 1 over minus z in the order, right? So that's only obtained when we have a plus sign in here. When we have the minus sign here, the order is not correct. Okay, good. So now all we need to do is to apply the inverse transformation using this equation in here. So we actually need to discuss for different situations, right? Because in here that the z is complex, right? Z equals to u plus iv, but we only care about the case where v goes to 0. So it's really the case where z equals to u plus I0. So now looking at this equation here, there are actually two cases. So the first case is that u is smaller or equals than minus 2, or u is greater or equals than positive 2. So this is a case where the square root of u squared minus 4 is greater or equal to 0, right? And that is the case where the m of z is real, which means that it does not have any imaginary part. So basically, it means that the rho of u equals to 0. Right, we don't have any probability mass outside this region. And next, for the second case, when we have u is in between minus 2 and positive 2, this is the case where the square root of u squared minus 4 is smaller than 0. And this is the case when m of z is complex, right? So if you look at this equation in here, right, so this is the case where m of z equals to the real part being minus u over 2, and then the imaginary part is I times square root of 4 minus u squared, right? And then we can finally obtain the density function rho of u. So that just equals to, so we just grab the imaginary part, and that becomes, and divide that by pi, right? We have the square root of 4 minus u squared over 2 pi. So that's it. That's exactly a semicircle, right? We don't have any probability mass outside this minus 2 and positive 2. And in between this, right, we have the probability density given by this formula in here. And that is exactly the formula for the semicircle. Okay, so this proof a little bit, it's a little bit technical, and we have gone through different parts, but let's not lose focus on the big picture. So let's do a summary. So we started off with the random matrix X, the Wigner matrix. Which is a pretty minimum setup for the random matrices. And then in order to derive the eigenvalues, we are looking at the resolvent. And by taking the trace of the resolvent, we have m of z. So this is the Stieltjes transform. which also can be represented as an integral of rho lambda over lambda minus z d lambda, right? So the key step for this derivation is that we are able to solve the m of z using the inverse formula. So we use Schur complement. Right, and once we solve that, we can use the inverse transformation from m of z to the density function rho. We can just use the inverse formula for the Stieltjes transformation. So that is the idea for the entire derivation. And for the next video, we're going to look at the Marchenko-Pastor distribution, which is a distribution for the eigenvalues of covariance matrix. This is more relevant for the principal component analysis because when we have noisy data, we're interested in the covariance matrix. The eigenvalues are related to the PCs, to the variance of the data. And in that case, it's also converged to a deterministic distribution known as the Marchenko-Pastor distribution. But the derivation will kind of follow the same structure in here, where we are going to use the resolvent and the Stieltjes transformations to solve for that distribution, just like the semicircle.